Share? Okay. Good. I'm gonna put showing on the thing. Can do this. Click here. What? It's not showing here?
It's not showing there.
Ah. Okay. It is. So we try again. Yes.
I'm trying to do look at those settings.
Okay. It's working in the test, huh? I did tested and it was working.
Yes, now it works.
Now it works?
Yes.
Okay. Good. Good. And
Yes.
it's everywhere? Okay.
Can you, yeah, and your audio is on.
My audio is on?
Put it on the pocket.
Okay. It's the audio is on here? Yeah. Okay.
Okay, last call of the session, and it's Said Rodríguez from Amos, and to talk about Max and also
Thank you for the introduction, and thank you to the organizers for inviting me to this nice location and a stimulating workshop. So, my name is Said. I work at AMOF. This is a research institute in Amsterdam. And what I would like to talk to you about today is the physics of fluctuations. And, I put it here in the context of AMO and condensed matter systems. And I think this is something a lot of us are interested in from various angles. So from the group of Jacqueline and Sylvain, there was this beautiful work on the physics of KP set, Carl Parisi-Sang equation implemented in a polariton lattice. Natalia was talking a lot about physics of fluctuations in the context of solving optimization problems, also in the context of machine learning. This paper she sort of briefly mentioned at the end, where she proposes to use the optical noise to accelerate some machine learning tasks. Oded and team have been working a lot on fluctuations in Kerr parametric oscillators with Javier as well and many others. And so the question that I would like to address today goes, it's a very general question that starts from the recognition that many of these systems, in fact, most of them, if not all, can be described by an overdamped Langevin equation, okay? So this is the overdamped Langevin equation. X involves all my degrees of freedom. F is a deterministic force, and this G of T is my stochastic force. And the deterministic force via Helmholtz decomposition contains basically two terms. One is the gradient of a scalar potential, and this is what I call the conservative force. And the other is the curl of a vector potential, and that's what we call a non-conservative force. And so every system can be written like this. So some examples from our community. My favorite system is a single mode Kerr resonator that was already discussed by Sylvain. And here you really need this non-conservative force. You cannot describe it as the gradient of a scalar potential only. A lot of people here work with cold atoms, so you may be familiar with Gross-Pitaevsky, stochastic nonlinear Schrodinger equation, truncated Wigner, complex Gimbus-Glandara equation, whatever you want to call it. At the end of the day, it's an overdamped Langevin equation that has this form, where the force is basically the Hamiltonian times the field, and the Hamiltonian can contain the nonlinearities, the dissipation. You can include coherent driving if you wish or not, and there is this stochastic term at the end. Here's a couple of systems that we have looked at in this context. These are the polariton systems, and this is this difield microcavities that the group of Martin Waits, for instance, is looking in the context of photon Bose-Einstein condensates. And so the question I would like to address in this context is whether there are any universalities in the statistics of systems described by overdamped Langevin equations. So we're going to look at statistical properties of these systems. And so the approach I'm going to follow may seem a little bit counterintuitive or surprising, but I hope you join me on the ride for a few minutes. And what we're going to do is we're going to get rid of the system. So we want to learn something about the system, but we're going to get rid of it. And so we're going to start by building intuition, getting rid of the force, setting it to zero, the deterministic. We're only going to have the stochastic force, and I'm going to make this as simple as possible, just a Gaussian white noise, okay, a delta correlated Gaussian white noise. So we're basically back to the physics of Brownian motion in a viscous fluid. Yeah, this is pollen grains in water, as first studied by Robert Brown almost 200 years ago. And so around 1940, Paul Levy came with this interesting works where he was looking at what's the fraction of time that a Brownian particle spends above the mean in a finite time trajectory. So this is an example of the displacement of a pollen grain in water, and you're seeing a trajectory of that particle in time. And so he was interested in the statistics of this shaded area under the curve, which is the fraction of time above the mean. And what he found is that the probability distribution of this quantity has this U shape, and the cumulative distribution has this arcsine function. Later, people asked two complementary questions, which was, what's the time taken to reach the maximum deviation from the mean? That's this red line here. And what's the last time at which the Brownian particle crossed the average? So that's T2, right? So we have 3 times now, T1, T2, and T3. And it turned out that also T2 and T3 have the same U-shaped probability distribution and this arcsine cumulative distribution. And so these 3 distributions became known as the 3 arcsine laws, or Levy's arcsine laws. And this is a beautiful example of extreme value statistics in the sense that the average here is the least likely to be observed, right? So the most likely values are at the extremes. So the particle will spend either all of the time way above the mean or all of the time way below the mean, but rarely half and half, right? Okay, so these arcsine laws have been studied and observed in many contexts. My favorite example is this competitive sports in basketball games. So if you look at distribution of lead times, so how they change, you find this U-shaped probability distribution. So when you're cheering for your favorite team, just remember you're observing random motion. Investment strategies based on the arcsine laws, shipping fuel prices follow the arcsine laws, interface growth. And there was this paper that caught our attention where they looked at distributions of work and other thermodynamic currents. And they found that they also follow arcsine laws. Okay, so now we're going to bring back the system. Hopefully you have now some basic understanding of these arcsine laws. And the question that we started with when we started in this problem is, now we bring back the system, so we don't have something very important change. We don't have free Brownian motion anymore, right? So we now have a fixed point because we have a deterministic force. And the question is, do the arcsine laws hold? And you know, it's not an easy question, actually. I have discussed it with mathematicians, and there is no analytical result for this. And the fact of the matter is they don't hold for alpha, for the field, which was we were looking before, so X. But if you look at the time-integrated field, or in this case, the time-integrated intensity, I'm now talking of an optical cavity, they do hold, and I'm going to show you that. Do the non-conservative force matter, right? And this non-conservative force is important because that's what sort of sets the difference with these previous works, that this non-conservative force makes the steady state non-equilibrium. Right? So if the force is purely conservative, meaning it can be expressed as the gradient of scalar potential, then the steady state is always guaranteed to be an equilibrium one described by a Boltzmann distribution. Otherwise, it's not. Detail balance is broken and the steady state is non-equilibrium. So this is a very simple experiment that we did. It's just a simple single mode linear optical cavity. We started from the very basics, as simple as it gets. And what we're doing is we're just scanning the detuning between the cavity and the laser back and forth across the resonance. And so if you measure a single trajectory, you see the black curve, and you do the average, you see the red curve. And we have a Gaussian white noise that we implemented here. So when the cavity is exactly on resonance, as I was telling you, we showed, actually this is a theory paper, we showed that you can describe the dynamics of the field in the cavity in terms of a purely conservative force that is derived from a scalar potential, and the steady state distribution is a Boltzmann distribution with an effective temperature given by the variance of the noise. So you do an effective equilibrium description exactly on resonant driving, right? So usually we hear in this community, I heard for many years, that if you're driven the sympathy, you're non-equilibrium. So we discussed in this paper that's not entirely true, okay? So it depends on where you are in the spectrum. If you go out of resonance, then the physics becomes non-equilibrium. And you see it in this picture, and essentially what happens is that this non-conservative force that is due to the detuning comes in. So you have a curl of a force that doesn't vanish. And what you have is something like Brownian motion in a stirred fluid. So basically, but instead of physical space, you have to think now it's in the phase space. You have this stir with a clockwise motion if you are on the negative tuning, and counterclockwise if you're in the positive tuning. The steady state is still Gaussian, but there is no Boltzmann distribution because there is no scalar potential that can describe your steady state. Okay, so that's our protocol. We're going in and out of equilibrium, back and forth. And as we're doing that, we're integrating the transmission of our cavity, and I build the trajectory of the time integrated signal. That's what I showed you here. And I remind you of the 3 times that I'm interested in. T1, the fraction of time above the average. T2, the last time of crossing the average. In T3, the time taken to reach the maximum deviation of the average. And if we do really like 100,000 of these trajectories we have to measure, you can build this very nice probability distributions, and you see all 3 times follow the arc-sine laws. This is the PDF, and on the right is you see the CDF. And this is a picture of Bashish, the PhD student who had the patience to measure 100,000 of these cycles. Now, what is really remarkable is that these arc-sine laws are extremely robust in the sense that it doesn't matter how far from equilibrium you are, so you can change anything about your system. You can change the tuning, you can change the laser amplitude, you could modulate 1, you could modulate 2, you could modulate neither. And in all cases, there is a universal convergence rate to the arc-sine laws. So the difference between the finite time distribution and the arc-sine distribution follows a power law with an exponent that is independent of the system parameters. So this is really a true sign of universality. Now, when we showed this work, we submitted this work, we got a lot of like comments from referees that, of course, this is trivial. It's because of adiabaticity. So then we say, okay, let's drive the system highly non-adiabatic. This is an example of a trajectory of the dynamics when the protocol is much faster than the relaxation time to the equilibrium, which is the inverse of the dissipation rate, gamma, and the arc-sine laws hold. So it holds even with non-adiabatic dynamics. Then they say, oh, yes, it's because you have a Gaussian steady state, right? So then we say, okay, let's bring in the kernel linearity. Then the steady state is highly non-Gaussian, it's a squeeze, classical, but squeeze. The arc-sine laws hold. Then they say, it's because you have additive noise, right? So if you have multiplicative noise, it will be spoiled. So we put in this multiplicative noise. This is a noise in detuning, which is multiplicative because it's multiplied by the field. It's fundamentally different. The difference between Ito and Stratanovich start to become significant. Arc-sine laws hold. Okay, so it's quite robust. And then the final one I'm going to leave for later, and this is the assumption of Markovian dynamics. That one is really important, and I'm going to address it at the end of my talk. So I now like to make a small intermezzo and say, okay, why should we care about these arc-sine laws, right? This very universal result that is applicable to all systems described by Overton-Langeron equations, include your favorite Brodsky-Taesky, Ginsburg-Landau, whatever. And then the second question, a little bit inspired by a discussion I was having last night with Ronnie and Oded, what is the value of the experiment? It's just a linear optical cavity. Why did we need to do this experiment? We could have just done the simulation and it would have been it. So I want to give you 2 answers to this question, and I'm going to show it explicitly through new experiments. The first one is because the context matters, and the context of optics is particularly important for the arc-sine laws, and I will tell you why. And the second is because it was really a stepstone for a more ambitious experiment where I'm also going to show we're going to address an open question that is very hard to answer through simulations. because of the time scales involved. Okay, and I will explain why. Okay, so about the first one, the context matters. So we started to think about the implications of these arcsine laws and these extreme value statistics. So this is an example of one of these trajectories of the time integrated intensity relative to the expectation value. Okay, it's kind of like it's the mean, but in the statistical sense. So that's this one here. And what you see is that this trajectory spends most of its time above the average, right? So it's on the right of that U-shaped probability distribution. And so you clearly see the time average and in this case, the ensemble average you would get from the expectation value are different, right? So ergodicity is broken. And we started to think, well, what implications would that have for optical sensing? And so what I mean is, you take an optical resonator, as many people use for sensing, right? You want to detect a molecule, or maybe you want to do computing with your optical system and you want to measure the time integrated intensity in all your complex array, right? And so then the question is, if you perform time average or you perform ensemble average, you get the same result, or is one better than the other? And here you clearly see that they're not the same. So, okay, we're going to look at ergodicity in optical detection. And so the question is the following. Suppose I'm going to make a single measurement of duration t, or I have the possibility to perform m IID measurements lasting t by m, okay? So I keep my measurement time constant. Then I can do either a time average in the first case, or I can do an ensemble average in the second case. And if ergodicity holds, they should be the same. But it doesn't. So this is an example of where this question is relevant. So people make optical sensors for all kinds of lab-on-a-chip applications, and they can make not one but an array of these resonators, and they can sort of send the laser into their chip and split it through an M output channel beam splitter and measure them all in parallel in order to get a higher throughput, right? And so this is how people do sensing in integrated photonics. And so then the question is, should I perform ensemble average or should I perform time average? There is an extra nuance of this question that I didn't mention, and that is that there is not one but two distinct ensemble averages. And so the starting point is that my resource is energy, not time, okay? And energy is the product of power and time. So what I could do is that I could either split the power and keep the time constant, or I could split the time and keep the power constant. But the point is that in both of these cases, I'm going to consume equal amount of energy as in the time average. Okay, so I'm going to keep my energy budget constant in all of these three cases. And what we find, this is results that were just accepted. They will be in physical review research in a couple of weeks, is that the sensing precision that you can attain under these three distinct averages, this is the time average, this is the constant time, where you have equal time as this one, ensemble average, this is the constant power ensemble average. So the precision that you can attain in sensing is quite different by orders of magnitude. So at short times, the constant power ensemble average outperforms the other two. And as the observation time increases, that's what on the horizontal axis, what you see is that ergodicity emerges, right? So ergodicity is really an emergent property of the system that emerges. You can see it in the limit of long times, or in the limit of large precision, which is when fluctuations are not so relevant, right? So if you want to really get this benefit of the ergodicity breaking, you need to go to either short times or small precisions below one. Okay, and the precision, sorry, I forgot to mention, is this. It's just the shift that I get in the resonance frequency of the cavity divided by the square root of the sum of the variances of the perturbed and the unperturbed cavity. It's a standard definition of precision. Okay. Last part about why do we need to do the experiment in the linear cavity that connects to the question of the necessity for the Markovian dynamics in these arcsine laws. So we have been working, my group, for a few years on this very interesting out-of-the-box system that still nobody works with, but hopefully one day it will be someone else besides us. So we had this crazy idea that we're gonna put it inside an optical cavity that's not poly. So we were putting all kinds of fancy semiconductors. We went to the shop, bought a bottle of olive oil, and really put a drop of it inside. And we're going to keep finding all this fascinating physics. So this is just some examples of things we did. The first paper we published on this was about the physics of scaling and universality in optical bistability. Then in this paper, we did broadband stochastic resonance. We recently realized the first superfluid of photons, not polarities. And it is the only superfluid that I know where the scattering was completely suppressed. I don't know any superfluid in any platform where they launch a fluid against an obstacle and they observe zero backscattering within a dynamic range of more than 3 orders of magnitude. So that was our experiment. We also realized the spiking neurons in this system. And all of the physics comes because in addition to this sort of fast kernel linearity, we have a slow nonlinearity that is a thermo-optical nonlinearity. Essentially, what this oil does is that it absorbs a little bit of the laser light. It expands because of this peak dissipation. The density decreases. Because of that, the refractive index also decreases. And so that's an intensity-dependent refractive index, which is kind of like a kernel linearity, but it's slow, okay? So there is a time scale here that is about microseconds. Yeah, perfect, thank you. Okay, so this is the equation of motion for the field in our cavity. Alpha is the field, delta is the detuning, gamma is the loss. This whole thing is the intensity-dependent nonlinear term, where K is a memory kernel that is exponential. This is the driving amplitude, this is stochastic force. And so now I'm going to do an experiment. I'm going to show you some experimental results where we're going to modulate the detuning like we did before for the arcsine loss on the time scale of seconds. Now, gamma is, inverse of gamma is picoseconds. That's the lifetime of photons in the cavity. But this memory kernel time, there is a time scale there that sits right in between at microsecond. And because of this term, there is no adiabatic elimination kind of trick, nothing that you can do that you will be able to get rid of some time scale. And if you do, please let me know, because we've been thinking about this for a while, and then you will see why I think it's not possible. So we're going to have dynamics spanning 12 orders of magnitude. Quite challenging to do numerically, I think. Okay, so I'm going to show you examples of trajectories of the time integrated intensity, like the ones that led to the arcsine distribution. And then I'm going to show you trajectories of the same observable, the time integrated intensity, in this oil field cavity. So on the left, these are the trajectories of the time integrated intensity. In the absence of memory, basically the cavity is just empty. We just have air, linear optical cavity. And you see that there are some of these trajectories that significantly deviate from the means. You don't see regression to the mean as you would see for a Gaussian process, but rather you see there's some spreading. But when we put in the memory, the dynamics look remarkably different, as you can see here. So there are these persistent currents. And essentially what you can already get intuition is that the rate of growth of the variance for these two processes are very different. Okay, so let's look at that. We're going to look at the rate of growth of variance of these two sets of distributions of the time integrated intensity. Without memory, it really doesn't matter if you have linearity or not, but the key point is that without memory, the variance grows linearly with time. So that's the hallmark of the diffusive process, like a Wiener process in particular is what we have. But when we put in this oil, then the variance grows with a power of 2 of time. So this is what is known as ballistic motion, ballistic transport. It's sort of a stochastic counterpart of what you would see in space in ballistic transport. Okay, then you can build distribution. These are preliminary results. They're not published yet. This is the probability distribution. And I now plot it in the log scale, because the mean is so unlikely that if I put it on a linear, you will just think that there is nothing there. So this is what's supposed to be the mean right at the center. And you see something very interesting that, well, basically you already see that the arc-sine laws are broken. To my knowledge, this is the first observation of the breakdown of the arc-sine laws. It's very sort of widely observed and universal phenomenon that I discussed in the beginning. But you also see that now these 3 times, they're not all the same. So sorry, I changed the names here. This was T1, T2, T3, but these names are a little bit more meaningful. So the blue and the red, they are T plus and Tm. So T plus is the fraction of time above the mean. So basically, they're roughly symmetric, these 2 distributions, because it's as likely that half of the trajectories will be above the mean and half of them will be below the mean. The same for the maximum deviation from the mean. But the last time of crossing 0, which is the average, notice it's highly asymmetric. And so what this essentially means is that this set of trajectories, they will cross the average at the beginning and then never again, right? And that's sort of what breaks the symmetry of these distributions. This is a theoretically open problem. We are looking for a theorist breaking off that would be interested in addressing this problem. It's non-Markovian dynamics, non-linear. Non-linear is not the easy part. So non-Markovian is the hard part. In a regime that involves 12 orders of magnitude in time in the dynamics, where you cannot apply central limit theorem, and once the limit theorem is broken, it's the core of the arc-sine laws. So if somebody likes or knows someone who would be interested to address this problem theoretically, please let me know. And with that, I would like to end. If I have, is my time really up, or do I have like 30 seconds? 30 seconds, okay. I didn't include a slide, but I just want to mention very briefly. I didn't include the slide, but I have it here. So we have this, besides doing crazy things like putting multiple localities, we also do more serious stuff. And so the serious stuff is that we put some unique semiconductors in a cavity that is in a closed cycle cryostat. So we built a closed cycle cryostat. This was a 6-year effort. And then we put a material that, you've probably heard that it's only bad because it bleaches, but it's super interesting. It's this perovskite semiconductor. And we can observe this optical bistability and hysteresis, kind of the thing that Silvano was showing. But it turns out that this material undergoes a series of structural transformations, phase transitions where the crystal lattice changes. And at a certain temperature, there is a phase transition, and what you see here is the strength of the nonlinearity. So this basically, by warming up the sample, we got a boost of sort of more than an order of magnitude in the strength of the nonlinearity. And I think this is sort of an interesting connection to the Paul atom people. That sort of the workforce has been always in special personnel or the continuing interactions. So to my knowledge, this has been the strongest tuning of nonlinearity in any optical system. The paper is in the archive now, if you're interested. And yeah, that's it. And I would like to finish, but that was my intermezzo of interactions. I would like to thank particularly Vashish Ramesh, who's a PhD student in the group who did the arc-sine laws on the weekend velocity breaking. And also the other stuff that I showed. We have a postdoc position if anything of this sort of thing interests you. And I would like to thank you for your attention. And I'll be happy to take questions. Yeah, the kernel is exponential. So this is the part that this is not the one that makes it last problem, I guess, tricky. So the kernel is exponential, and because it's exponential, then you can write this integral differential equation as a set of ordinary differential equations in one higher dimension. So basically, your count is only non-Markovian because there is a degree of freedom you're not looking at. And that's actually the temperature of the oil in the cavity. But once you put in the exponential here, you can integrate this term and you get an extra equation of motion for that degree of freedom is the temperature, and then the whole system is Markovian. But then we keep seeing this non-Markovian physics, right? So yeah, this is the tricky part, and we are not sure yet how to understand this. Yeah.
You have any way of controlling the non-Markovianity?
Yeah. So it's a great question. Do we have a way to controlling the non-Markovian? So non-Markovian term is the nonlinearity. The nonlinearity has two properties. One is the strength and the other is the time. So the way to control it is in that final intermezzo that I showed you at the end, where we have this crystal, peroxide crystal in the cavity, and by varying the temperature, we can drive this system near a phase transition where you can get an enhancement of the state. But there is also something like a critical phenomenon there going on. We don't really understand it yet, but yeah, we think that basically the way is by pulling the material that you can drive it close to critical points where you have some divergence of the reaction in the system needs to change the time scale of the memory category. That's what we're doing.
We are already in the time, so let us say Said and all speakers of the session. That one answering to the